Hey everyone, and welcome to The Explainer. Today, we're diving into a genuinely fascinating intersection, the place where the physical objects we touch every single day meet the cutting-edge world of digital AI training. We so often think of artificial intelligence as this thing that exists purely in the cloud, right? Just crunching text or generating flat 2D images. But for AI to actually interact with our real, physical world, for robotics to become truly functional in our homes and our factories, well, machines have to understand the tactile objects around us. And that brings us to the surprisingly complex, highly specific world of industrial design and everyday controls.
So think about this. How exactly do we teach an AI to turn a dial? I mean, it sounds like such a simple, basic human action. You just reach out, grab a knob on a stove or a piece of machinery, and you twist it. Easy. But for a machine, that is incredibly complex. It requires understanding 3D depth, identifying grip patterns, and performing what engineers call state estimation, basically knowing exactly what angle that dial is currently set to. Getting machines to actually understand these everyday human interfaces requires a very specific, totally pristine kind of data.
All right, Section 1, inside the Codatta Dataset, High-Fidelity Industrial Design. This dataset, which is curated by Codatta, is a high-resolution collection entirely focused on electrical appliance knobs and rotary controls. It's built specifically to support fine-grained object understanding. We're not just giving an AI a picture and saying, hey, this is a stove. We're zooming way, way in. We're looking at the actual industrial design of the controls themselves, capturing those intricate little details that a robotic hand or a computer vision system would literally need to interact with that specific component. And let's look at the first key metric to wrap our heads around here: 408. There are exactly 408 meticulously paired training samples in the trained split of this dataset. Now, I know what you're thinking. In the world of big data, where we're constantly hearing about billions and billions of rows, 408 sounds tiny, right? But the value here isn't in massive volume. It's in hyper-curated, high-fidelity quality. Every single one of these 408 entries is a highly specific, unique identifier for a particular knob or appliance sample. Now follow me on this next number, 1.74 gigabytes. If we only have 408 rows of data, but the dataset itself is nearly 1.74 gigabytes, what does that actually tell us? Well, to put it simply, it proves just how incredibly high resolution this imagery is. That is some serious data weight for 408 items. We're talking about exceptionally detailed images where every single ridge, every printed number, and the exact material texture is captured perfectly. It is absolutely a case of quality over quantity, precision over sheer volume. So how do they actually maintain that level of quality? Well, they have strict standards. First, every single image is perfectly clear and unoccluded. They've been manually verified to ensure the knob is the absolute primary focus. That means no hands, no distracting wires in the background, and no other random objects blocking the view. Because think about it, if you want to train a robot, you can't have a human hand in the reference photo messing up the algorithm, right? On top of that, they use incredibly consistent lighting across the board to really highlight the textures and markings. It's pristine, robotics-ready data. Which brings us to Section 2, the power of two views, the anatomy of the data. The source material really hits the nail on the head with this quote: "Every data entry captures the same specific knob from two distinct and correlated angles." And guys, this is the secret sauce. By giving an AI two correlated angles of the exact same object, you're essentially giving it stereoscopic vision. You are allowing the computer to correlate information from totally different viewpoints, which is exactly how human eyes naturally perceive depth and shape. To break that down a bit more, you start with the front view, or image 1. This is your direct frontal shot. It shows the face, the position indicators, and the markings. It basically tells the AI, okay, what is the style actually set to? But then you contrast that with the side view, or image 2. This is a profile or oblique angle, and it is absolutely crucial. It shows the depth, the height, the material texture, and most importantly, the grip patterns. If a robot needs to physically grasp a knob, it definitely needs that side view to know exactly how far the knob sticks out and what kind of texture its grippers are going to encounter. Both of these views working together are absolutely necessary for true 3D understanding.
Moving right along to Section 3, Empowering Robotics and AI, moving from data to application.
So, what can developers actually do with this? Well, the dataset supports several clear, practical tasks. First up is multi-view object recognition, identifying objects using that correlated information we were just talking about. Then there's 3D shape reconstruction, where models can infer the entire 3D structure and depth based purely on those front and side profiles.
Next is knob state and angle estimation. This one's wild. It's literally training models to read the precise setting or angle of a dial. Imagine a factory safety robot that can just look at a complex control panel and instantly know if a critical pressure valve is set to high or low. We are directly connecting the micro details of a knob to massive, real-world macro goals.
Actually, I want to pause for a second and clarify one really specific use case we just touched on: generative AI training. This dataset serves as incredibly high-quality reference data for training LoRa's or control nets. And if you're into AI image generation, you know those are powerful fine-tuning tools that guide the AI's output. Because let's be real, it's notoriously hard to get an AI to draw a perfectly functional, mechanically accurate machine part. But by feeding models this dual-view, highly standardized data, it acts as the ultimate reference point. It helps next-generation AI models generate specific industrial components that actually make logical, structural sense.
All right, Section 4, Access and Implementation, Getting Started with Python.
Now, because this data is stored in a highly efficient Parquet format, pulling it is blazing fast. The source actually provides this super digestible 3-step Python magic trick to get you going. Step 1, you load the dataset using the Dataset's library, specifically pulling Codatta Appliance Knobs, dual view right from the train split. Step 2, you grab a single sample entry, literally just calling sample equals ds bracket 0. Step 3, you visualize the front versus the side view using matplotlib, setting up a simple side-by-side plot. It is remarkably straightforward to bring this high-resolution dual-view imagery straight into your own coding environment.
And honestly, the best part? This dataset is released under the OpenRail license. This is an open access licensing framework, which means this multimodal dataset with all of its high-resolution imagery and perfectly formatted data is just out there. It's readily available for community use, computer vision research, and robotics development right now.
Which really leaves us with this final provocative thought. If AI can now master the intricate 3D nuances, the grip textures, and the precise state estimation of a simple appliance dial using just 2 correlated images, what physical interface is it going to digitize next? The bridge between the physical and the digital is literally being built right now, one high-resolution dataset at a time. I really hope this explainer sparked your curiosity and gave you a great structured understanding of how machines are quite literally learning to see our world. Keep exploring, keep learning, and we'll catch you next time.